folks, we're back and let's continue. And let's now talk about memory. So, the first question asks issues in memory management, speed and protection. Be able to describe the issues. How do we achieve speed and how do we achieve protection? So, let's go ahead and let's talk about that. So, when it comes to speed, we want our memory to be as speedy as possible. So, in other words, we want our memory to be fast. I would actually add to this a little bit. I would say we want our memory to be both large and fast. But unfortunately, as we have learned previously, the bigger your memory becomes, also the slower it becomes. Why? Well, because that's just how the memory architecture works. Okay, uh, th- when you start adding more and more memory-related circuitry, it becomes slower. So, but we want our memory to be both big and fast because we're humans. We want our cake and we want to eat it. We want to eat it too. So, and another issue is protection. So, on your system, you have many processes running at the same time, and each process gets its own memory. And you want to make sure that each process can only access its own memory and it cannot access the memory of other processes. If it tries to, it needs to be stopped. So let's talk about that. So we have already mentioned that the two issues are speed and protection. So first, let's talk about speed. So as we have learned before, the memory in a computer is typically organized in a hierarchy. At the bottom of the hierarchy, you have larger and slower memories, and as you move up, the speed of the memory increases and the size decreases. Also, the price of the memory increases as well. So, for example, the fastest memory is the registers of the CPU. They're extremely small. On a 32-bit architecture, they are 32 bits in size. In 64-bit architecture, they are 64 bits in size. So very small. Then there is something called the cache memory. The cache memory is the specialized memory to cache the contents from the main memory. The main memory is your RAM, and the cache memory temporarily stores things from the RAM for faster access. And this can go on for multiple levels, the cache memory specifically. So you probably heard about L1, L2, L3, right? So those refer to the cache level. So there is an L3 cache, then L1, and then L3, L2, and L1. Okay, so multiple levels of caches, and each cache caches the data from the cache right before it. So it is possible that, for example, the piece of data from the main memory might be cached in the cache memory, and then data from that cache can be cached in another level of cache right here. So if I access the data, for example, very often from the main memory, I can cache it in the cache memory. And if I exit often from here, then I can also cache it in another level of memory. There are basically two considerations that drive the algorithms that decide what to cache where and when. They're basically the spatial and temporal proximity. Spatial proximity basically means that when I access a memory address, it is highly likely that pretty soon I'll be accessing the memory addresses that are close to that memory address. So one example of that is an array, right? What is an array? An array is just a bunch of memory locations, one after the other. So when I access one memory location in the array, it is quite possible that very soon I'll be accessing the adjacent location in the array. As an example, consider a loop which goes through the array, right? So, and another one which I mentioned was the temporal locality, and the temporal locality, it refers to the time. Okay, so if I accessed an item just now, it is highly likely that I'll be accessing that item again in the near future. So like once again, I think a loop is a good example, because if I have a loop control variable, for int equals I is less than 100, I plus plus, well, that loop is going to repeat 100 times. So if I access the variable I'll be accessing it again pretty soon. So those two principles, they drive to decide what to cache, where and when. So I want to cache things that exhibit spatial and temporal proximity. Okay, so let's write this down. So the speed issue is addressed through caching. So caching temporarily stores data from the slower memory in the faster memory. The decisions to cache data are typically based on the temporal locality, meaning if the data was accessed, it will soon likely be accessed again. Okay. Again, and based on the spatial locality, which means that if the data, are you trying to tell me I'm wrong here, Word or OpenOffice? So it will soon likely be accessed again. So if the data was accessed, the data in the nearby memory will likely be accessed again. For example, an array. Okay, so that's basically the idea. One of the issues associated with caching is cache consistency, which is basically making sure that the data is consistent across all levels of the hierarchy. Okay, like that. And so basically, let's say that I take a data from the main memory and I temporarily cache it in the cache memory. And let's say that I update the data in the cache memory. What's going to happen then? Well, we need to make sure that if somebody accesses that same data from the main memory, that that data will have the same up-to-date value as the value in the cache memory. Okay, that's basically the idea. Another issue is protection. Okay, so in protection, we need to make sure that a process doesn't access memory that doesn't belong to it. So I'm going to say the protection issue is making sure that the process cannot access any memory outside of the memory that is authorized to access. So the basic approach is to use the base and limit registers. The base register stores the address where the process begins in memory, and the limit register stores the process memory size. The process may access any memory address in the range of, so basically it can be less, it can be greater than or equal to the base register. Okay, so address, and it has to be less than the base plus limit. Okay, base register plus limit register. Okay, this works only in contiguous memory allocation schemes. Other schemes are possible. Other approaches are needed in, e.g., paging or segmentation schemes. More segmentation than paging. Okay, so that's basically the the idea. Okay, so now let's take a look at the example of this. So let's say that we got a bunch of processes, and this is how the memory layout looks like. So in the first location of memory, we have the operating system, which goes until 255,999, and then at address of 256,000, we have another process, and let's say currently the executing process is this one. So the base register is going to be loaded by the operating system to contain the starting address of the process, and then the limit register is going to be loaded with the memory size of the process. So once again, as we talked about, this means that the process can access any memory location from 300040 all the way up to base plus limit minus 1. So in other words, any location up to 420,939. Okay, that's basically the idea. Okay, that's how we do it. All right, now let's take a look at the hardware which we will need in order to be able to implement this kind of a memory protection scheme. So a process will be executing on the CPU, and it'll be requesting to access addresses. So the first thing which we'll do is we'll check to make sure that the requested address is greater than or equal to the base. In other words, we're checking over here to make sure that the process doesn't access any address that is below its lower bound, okay, which is the address stored in the base register. And if that's not the case, then this is a fatal error, and usually the process would be terminated. If the address is greater than or equal to the base address, then we're going to check, is the address less than base plus limit? So once again, we're basically checking to make sure that the address does not fall outside of the upper bound. And the upper bound is always base plus limit minus 1. And if that passes, then the process is permitted to access the memory location. Okay, so that's the basic idea. All right. So any questions? So and then, okay, so caching, how does it work? Okay, so I'm going to, so I kind of already answered it in the previous one, but I will answer this one explicitly. So caching works by temporarily storing the data from the larger but slower memory in the smaller but faster memory. Okay, the caching the memory caches are hierarchical with the largest and slowest memories at the bottom and the smallest / fastest memories at the top. Okay, so the decisions to cache are based on spatial and temporal localities. Okay, and basically I'll just copy this part. So one of the issues which is created here is the cache consistency problem. Okay, where once again we store something in one level of the hierarchy and we update it, and we need to make sure that if somebody accesses it from another level of the hierarchy, that they will see the same up-to-date value of the data. That's cache consistency. Okay, and then the other question here was about memory protection. What hardware support is necessary for the basic memory protection? And once again, I addressed it in that top question, but I will put it right here. Okay, so I'll just copy it and paste it. Okay, so that's basically the idea. Once again, we need a base and a limit register, and the process can access any address between the address in the base register and the address in the base plus limit -1. Okay, so the base register stores where the address starts, where the process starts in memory, and the limit register stores the size of the process memory. Okay, that's basically the idea. So the next question asks us about binding. So what are the different approaches to address binding? What is the difference between compile time, load time, and execution time? Which binding scheme allows process to be relocated in memory during runtime? Which scheme is more efficient? Which scheme is more flexible?
Next question is the memory protection one.
Oh, I think I answered that one. No, let me check. Yeah, I answered that one. Yeah, right here. Yeah. Basically, I have addressed it up there, so I just kind of copied it and pasted. So yeah, I might have gone a bit fast, so I'm sorry. Yeah, but I did address it. Basically, I'll go through it again. The basic hardware for the basic memory protection is that you need a base register, which stores the lowest address that the process can access. And you have a limit register, which stores the size of the process memory. And then the process can access any memory address starting from the base register up until base plus limit -1. Okay, so access of any other memory location that is outside of those bounds is treated as an invalid memory access. And typically the process would be terminated. Ooh, I invented a new word. That can be a meme, you know. So, and next we have address binding. Okay, so let's talk about address binding. And this question consists of multiple questions. So let's address them one by one. So first, let's do a high-level discussion of binding. So as we talked about in class, there are three approaches to address binding. So first of all, what is address binding? So address binding is basically deciding where is figuring out the addresses of every variable and instruction in your program. Or to put it more broadly, each instruction and data item in the program. So let's begin by defining it. So address binding is deciding where in memory will each instruction and data items will be stored. Okay, so there are three main types. There is compile time, load time, and execution time binding. Okay, binding. Okay, so now let's talk about each one of those. So first, I'll talk about what they are, and then we'll go back and we will rank them according to the efficiency and flexibility. So first, let's talk about compile time binding. So basically, during compile time, the compiler figures out the address of each instruction and data item. So I will say specifies the address of each instruction and data item. When the program is executed, it must reside at the memory location selected by the compiler during compile time. If we wish to store the program in another memory location, we must recompile it. Okay, and I think you can already tell from this that this is not at all flexible. Okay, very inflexible. Now, and then the second one is load time binding. So in load time binding, the address of each instruction and data item are determined when the program is loaded into memory. So in this case, the compiler assumes that the program, I'll say that the process will start at memory location, I'll call it B, but does not specify the actual value of B. Okay, each instruction, the address of each instruction and data item is specified as an offset from B. For example, instruction stored at address of B plus say 4. Okay, when the program is being loaded into the memory, the loader, the component of the operating system that loads programs into memory, will select the value of B, and the addresses of all instructions and data will then be computed based on B. For example, the instruction will be stored at B plus 4 equals, say 100 plus 4 equals 104. Okay, assuming that the loader picked the value of B that is 100. Okay, So if we wish to store the program in a different memory location, we must reload it, okay? So basically in this case, we just have to terminate the program and reload it. And hopefully the next time around, the loader is going to pick another base memory address where we can store the program in memory. So more flexible than the compile time, because in compile time, the only way to change where the program is stored in memory is to recompile the program. Here, we don't have to recompile the program. We need to reload the program, okay? And I'll add, in this case, the compiler generates what is referred to as the relocatable code, okay? And then we have execution time binding. So in execution time binding, the address of each instruction and data item is determined when the program is executed. So this allows the program to be moved in to change its memory location during runtime. So let's compare those in terms of flexibility. In compile time binding, I have to recompile the program, so very inflexible. In load time binding, if I want to change the memory location of the program, I have to basically terminate the program and restart it so it'll be loaded at the different address, perhaps the address where I want it. The execution time binding, you don't have to really do anything. The program can change its addresses. It can change where it is stored in memory during runtime. And we don't have to do anything, okay? So, and I will, yeah, so, and then in terms of efficiency, yeah, and I'll talk about efficiency in a second. Now let's address the issue of flexibility. So runtime is the most flexible. The runtime binding is the most flexible because the program's location can be changed during runtime. The load time binding is the second most flexible, as changing the address of the program amounts to reloading the program. And then compile time binding is the least flexible, as it requires the program to be recompiled if its memory address is to be changed. Okay, so this is the flexibility. Now, in terms of efficiency, let's talk about efficiency. So when it comes to efficiency, the compile time is the most efficient, since the compiler computes all of the addresses, and neither the loader nor the CPU have to do anything related to address computation. Okay. Now, so basically, loading / execution is fast. Then load time is the second most efficient, as the loader computes the addresses, but no address computations are necessary during runtime. And finally, the runtime binding is the least efficient, since it requires that every memory access is translated. Okay, so that's basically the idea. And the runtime is the most popular approach. And examples of those schemes would be, paging, segmentation, and the other schemes which we learned about. Okay, so that's basically it. Did I address every single point? Yeah. All right. Does this make sense? Okay, great. And Carl's asking, which binding scheme allows the process to be relocated in memory during runtime? That's the execution time binding, or the runtime binding. That's this one. Okay. So the program can change its memory location during runtime. Oh, I wrote it down right here. Yeah. So, yep. All right. So that's basically the idea. Do we have any other questions? And then the next question asks, address spaces, what is the difference between a physical and a virtual address space? Which address binding scheme will the two be different? Okay, so let's talk about that. So this is compile time, runtime, execution time. So basically, the virtual address so the virtual address is the address generated by the CPU, aka the address issued by the process executing on the CPU. Okay, so that's basically the idea. The physical address is the address accessed by the MMU, by the memory management unit, or the MMU, or right? So the memory management unit. So cows go moo. So, and then whose job it is to perform the memory accesses. Okay, so in compile time and load time binding, the physical address will be equal to the virtual address, while in the runtime binding, the addresses may differ. Okay, so that's basically the idea. So this is because in load time, I'll say compile time, and load time binding, the addresses of the processes in physical memory are already fixed by the time the process gets to execute. This is not the case for runtime binding, because the process may move around in memory during execution. Therefore, the virtual addresses provide a consistent way for the process to access its memory contents without worrying about the changes to its physical, about the changes of addresses resulting from the process being moved to another memory location during runtime. Okay, that's basically the idea. So just to make that a bit clearer. So for example, let's say that we have a process, okay? So in load timing or compile time binding, the memory locations of every single thing will be known. So the process may have an instruction, jump to address 1000, okay? And it'll jump to the actual address 1000 in the RAM, okay? Now, let's say that the process is moved to another memory location. Well, then the address of the location to which the process wants to jump might no longer be 1000. It might be something else now, since we moved the process in memory. So in order to avoid those kinds of issues, we will let the process have what's called a virtual address space. So the process will always assume that its memory starts at 0 and goes up until some maximum address. And the process will be accessing all of its instructions, all of its data as an offset from 0, okay? And the memory management unit will be responsible for translating those addresses to the actual physical addresses in RAM. So in runtime binding, typically all of the addresses will be virtual. So when the process says, I want to jump to location 100, it is referring to location 100 starting from the beginning of its address space. The process itself has absolutely no clue where in memory it is stored, nor does it care. All it cares is that it says, in my program, I want to jump to location 100. Now, if the process is stored in memory location 14,000, this is the physical memory location, it's not saying it wants to jump to the physical memory location of 100, which would probably locate it somewhere right here. It wants to jump to location 100 with respect to where it starts in memory. So the memory management unit is going to translate the virtual address, which is 100, into the physical address by adding the virtual address of the process to the starting memory location of the process. So what is going to happen is that the virtual address of 100 will be translated to the physical address of 141.0.0. Now, let's say that while the process is executing, it gets shifted down in memory to this location. So now its starting address is going to be 1500 instead of 1400. Well, inside its program, the process will still say, I want to jump to location 100, because once again, it wants to jump to location 100 starting from the beginning of its memory, okay? And the memory management unit at that point would store the new memory location of the process in memory, and it'll now translate the virtual address of 100 into physical address by doing 1500 plus 100, which will give us the physical address of 15,100. Yes. 15,100. Yep. So that's basically the idea. Okay. So I said it was going to be moved down to the location of 15,000. So 15,000 plus 100 is going to be 15,100, right? Yeah. There we go. All right. So that's basically the idea. And another thing to remember is that each process will get its own virtual address space. So processes always work with virtual addresses, and each process assumes that its addresses start at address 0 and span until some maximum address. Okay, so the address of 0 is equal to the address, a virtual address of 0. The virtual address of 0 is equal to the physical address of in RAM where the process starts. For example, if the process resides in memory location, say 14,000, then a virtual address 0 equals to the physical address of basically 14,000. Okay, a virtual address of say 10 is equal to the physical address of 14,000 plus 10, which is equal to 14,010. Okay, that's basically the idea. So and then so all processes will have a virtual address, will have a virtual address of 0 that of 0 max. However, for each process, this addresses will be mapped to the different physical memory locations. Okay, like that. So for example, a process has two processes, P1 and P2 reside at 14,000 and at physical locations, or 40,000 and 15,000 respectively. Okay, virtual address of P1 of 0 of P1 is equal to physical address of 14,000 and 50,000 and virtual address 0 of P2 is equal to 15,000. Okay, like that. All right, that's basically the idea. So, and then and this is what I talked about. The job of the MMU is to translate from virtual to physical addresses. So the job of the MMU is to perform this translation from virtual to physical addresses. Okay, that's basically the idea. And this is how the translation is actually performed. So you have a process that executes on the CPU. And when the process executes on the CPU, the relocation register inside the MMU. So the relocation register is the register in the MMU that stores the base physical address of the currently executing process. So, and whenever a process generates a virtual address, the MMU will translate it into a physical address by adding the virtual address to the relocation register, which once again stores the physical address of the process of the memory location where the process starts in memory. So if the process starts at a physical memory location of 14,000 and a process executing on the CPU issues a virtual address of 346, we get a physical address by adding 346 to 14,000, thus giving us the new physical address. All right, that's basically the idea. So, and then the next question asks, dynamic versus static linking. What are the ups and downs? So let's talk about that. Okay, so linking is combining the library with the program code. This can be done either statically or dynamically. So this can be done either using static or dynamic linking. Okay, so the static linking integrates all of the library code. I'll say combines the library code with the program code in the resulting executable. In other words, the executable carries a copy of the code of all the libraries that it needs. Okay, so this helps to the program to be portable. It will run on any compatible system, regardless of whether the system has copies of the libraries the program needs. Okay. At the same time, it bloats the sizes of executables executables, as each executable carries the library code, carries copies of library codes. Also, if the library needs to be updated, for example, as a result of a bug fix or a security vulnerability update, the program has to be relinked. Okay. Now, in dynamic binding, in dynamic linking, no codes, no library codes are included in the executable. Instead, the executable includes code stubs that tell the loader how to find and load the libraries that the program needs. Okay, this helps reduce the size of the executables and also reduces the memory consumption because one copy of the library code can be loaded into memory and then be accessed from there by all dynamically linked programs that need it. Okay, so that's basically the idea. At the same time, this also means that new libraries, that the program can make use of updated libraries without the need of being relinked. Okay, and at the same time, the program loses portability because if the target system does not have the libraries the program needs, the program will not run. Okay, so that's basically the idea. All right. So, and then the next question asks us, what is process swapping and what are the requirements of process swapping? Okay, so let's talk about that. So, process swapping basically refers to temporarily swapping the process into the disk from the memory in order to free the memory for the current processes or the new processes. So for example, let's say that I'm running low on memory, so I can temporarily take one of the processes that isn't doing anything, is just waiting. I can temporarily swap it onto the disk, and then I can bring it back later. And the requirement for this is that I have to have some kind of a backend store, such as the disk, in order to be able to swap the processes. So basically, this one is straight from the slides. Okay. Okay. So I'll say a requirement for this for swapping to work. Okay. Okay. That's basically the idea. So okay. And then we have the next question, the contiguous memory allocation scheme. What is the difference between the fixed memory allocation scheme and between fixed and variable memory allocation schemes? So let's talk about that. So basically, the fixed partition scheme splits the memory into a bunch of fixed partitions, and a process is assigned a single partition. One of the challenges is internal fragmentation. Is internal fragmentation, where the partition space not used is the partition space wasted. Okay. So okay. So it is the partition space wasted, and then the variable allocation scheme is where each process is inserted into any memory hole available. When the process terminates, the memory hole is free. One of the challenges is external fragmentation, where there is sufficient overall memory. A problem where there is sufficient overall memory to store the new process, but no memory hole is large enough to store the process. So let's go ahead and let's review that. And once again, all this is straight from the slides. Okay. So, and we have a question. What requirements and advantages are of process swapping? So I already mentioned it. A requirement is backend store. We need to have some kind of a backend store like the disk. Okay. And the advantages is that it allows us to free memory for use by other processes. So I can temporarily remove the process from memory onto the disk to make more room for other processes. Okay. Make sense? All right. So that's basically the idea. Okay. So let's go ahead and let's review that. Yeah. I don't know, folks, if you find it helpful, because I feel like you're just being bored to death by watching me retype the slides. But if it's helpful, that's fine. Okay, so first, let's take a look at the multiple partition allocation scheme. This is the variable partition. So let's take a look, at the variable partition allocation scheme. So basically, like we talked about in class, here is my memory, and my memory is full of processes. So the operating system is at the lower addresses, and then there is a process 5, process 8, and process 2. And let's say process 8 terminates, so this will leave a memory hole right here. And let's say process 9 starts up. Process 9 can fill the upper part of the hole. Then let's say that process 10 starts up and it can fill another part of the hole. And one of the challenges which we talked about here is external fragmentation. So external fragmentation is when the process is requires a certain amount of memory, and if we add up the sizes of all the holes, the overall amount of memory is sufficient to store the process, but no individual hole is actually big enough to accommodate the process. So what are some things which we can do as we try to fit the process into the memory? So there are 3 solutions to fitting a process into the memory. One is called the first fit, and basically the idea behind first fit is we're going to allocate the first hole that is big enough. There is the best fit, which will allocate the smallest hole that is big enough, but it will require searching the list to find the smallest hole that is big enough to fit my process. And finally, there is the worst fit, which tries to find the largest hole that can fit the process. So, and generally, the first fit and the best fit give the best results in terms of speed and the memory utilization. And the best fit generally gives the fastest performance, okay? Faster than the first fit. So that's basically the idea. Now, the next question asks us about compaction. So when it comes to compaction, and this is used in the variable allocation scheme. So compaction is basically the process of, so compaction is used to deal with external fragmentation by by rearranging the processes in memory in order to merge all of the holes into one big hole for storing the new process. And the problem with the approach is that it is very inefficient and requires that processes and requires that the system uses runtime binding, because we will be moving the processes in memory, okay, like that. So that's basically the idea. And then we already talked about this for the variable partitions. There is the first fit, best fit, and worst fit. So we talked about that already. And that's basically right from the slides. So once again, it's basically this part. So once again, first fit, find a memory hole that is take the first memory hole that is big enough to store the process and store it there. The best fit, find the smallest hole that is big enough to store the process. And worst fit is find the largest hole that is big enough to store the process. Okay. And once again, according to the simulations, first fit and best fit give the best speed and memory utilization, whereas the best fit is generally faster than the first fit. Okay. So, and then, okay, so what is the difference between internal and external fragmentation? So we have kind of discussed this already indirectly. So internal fragmentation is when there is happens in the fixed partition scheme, okay, where the memory is split into multiple fixed-sized partitions. And one process is assigned to a partition. Okay. The memory, the partition memory unused is the memory lost to internal fragmentation. Okay. And external fragmentation is when happens in the variable partition allocation scheme, where there is sufficient overall memory to store the new process, but no individual memory hole is large enough to store the process. Okay. So that's basically the idea. So, and then next, we talk about pages. So would you guys like to take a little break before we talk about pages and the new stuff in the video? Or would you like to just keep going? How do you feel? Okay, so you'd like a break? Okay, yes, so let's take a 15-minute break, and then we'll come back and we will continue. Okay, so take a break. So we stopped at the discussion of page tables. What are they and how are they used? So before we can answer this question, let's review paging. So basically, paging works as follows. So basically, in paging, the physical memory is broken into the fixed size chunks called frames, and the virtual memory is broken up into the fixed size chunks known as pages. So typically the size of the page and the size of the frame, they are identical. So, and the advantage of paging is that it permits the physical address space of a process to be non-contiguous. So in other words, before we always assumed that all of the process memory is stored contiguously. This paging allows the process memory to be non-contiguous. So in other words, one part of process memory can be stored in one part of memory and then the other in the other part of memory. In other words, the process memory does not have to be contiguous. All right. So I'm going to divide the process memory into a bunch of pages, and then each of those pages can refer to a physical frame that is located in basically any physical memory location, does not have to be in a contiguous memory location. So also, this paves the way for approaches which allow the process to allocate more memory than there is physical memory available, or it allows the process to allocate memory um, whenever the physical memory is available. And because paging splits memory into fixed size chunks, there is no external fragmentation. So let's talk about how paging generally works. So in paging, whenever we want to access a particular address, we access it in terms of the page number and the page offset. So first, let's take a look at how paging works on a high level. So the virtual memory of the process will be split into a bunch of pages. So as always, the virtual memory space is assumed to start at address 0, and it goes until some maximum address. So the virtual address space is going to be split into pages equal sized, and whenever a process wants to access a certain address, it will be defined by the page number of the page on which the address falls and the offset within that page. Now, although the virtual pages are always contiguous, the physical frames in the physical memory that actually store the data, they don't have to be contiguous. So for example, the physical frame that stores the data from page 0 is stored in a physical frame location 1. The physical frame that contains data from page 1 is stored at a physical frame 4. The physical frame that stores data from page 2 is stored in the physical frame 3. And finally, the data from page 3 is stored in the physical frame 3. So the key idea here is you see how the process memory can be split into pages, and the different pages can be stored in physical frames all throughout the physical memory. They don't have to be stored contiguously. The process thinks its memory is organized contiguously, but in reality, it is not. So how do we translate from the virtual page to the physical frame in the physical memory that actually contains the data? This is where the page tables come in. So the page table is used to translate from the virtual page number to the physical frame number. So typically, a page table is indexed by the virtual page number, and each index location stores the corresponding physical frame. So for example, if I want to know the physical frame associated with page 0, I index into location 0. I see that the value of this location is 1, so I know page 0 is mapped to the physical frame 1. Similarly, with page 1, I index to the location 1, and it's mapped to the physical frame of 4. Okay? Page 2 is mapped to the physical frame of 3, and page 3 is mapped to the physical frame of 7. Okay? That's basically the idea. Now, So the way in which this will work is as follows. So when the process is executing on the CPU, it'll generate a virtual address just like it did before. It'll say, for example, I want to access address, for example, 100. So let's say that that address 100 falls somewhere right here. Well, this address will be split into the page number, which will be page number 1, and an offset location, which is the offset within this page. So it will look like this. Okay, so we get the physical frame number from the page table that is associated with the page, and we then map it to the physical frame and then the offset. So once again, process executes on the CPU, issues an address. That address is split into the page number and into the offset within the page. So the page number is used to index into the page table, and from the page table, we get the physical frame number, or the physical frame that stores the data from the specified page. And then we access that physical frame number in RAM. And inside the frame, we access this offset. Okay, that's basically the idea behind paging. So the page tables are used to translate from the virtual page number to the physical frame number. Okay, that's basically the idea. Okay, so, and then the next question asks about the TLBs. Well, first, before we talk about the TLBs, let's expand and let's talk a little bit more about paging. So how is paging actually implemented? How do you take an address and how do you split it into the page number and offset format? So here is an example. So let's say that the process has 16 bytes of memory. Okay, 16 bytes of virtual memory space. So this means that the process can access, every process in the system can access any address, any virtual address from 0 to 15. There is also a physical memory, a physical RAM, whose size is, it looks like 32 bytes. So let's say we decide to use 4-byte pages. So the size of each page is going to be 4 bytes. Well, if my process virtual memory is 16 bytes, then 16 divided by 4 is going to be 4. Therefore, my process has 4 pages, okay, 4 virtual pages. How many physical frames are there going to be? Well, if the process physical memory is 32 bytes in size, then 32 divided by 4, the size of a single frame, we get 1, 2, 3, 4, 5, 6, 7, 8 frames, right? Because 32 divided by 4 is going to be 8. Now, how are those pages mapped into the physical frames? Well, this page table tells us how. So page 0, which is this page, is mapped to the physical frame 5. So 0, 1, 2, 3, 4, 5. Okay. The virtual page 1 is mapped to the physical frame of 6. So 0, 1, 2, 3, 4, 5, 6. The virtual page 2 is mapped to the physical frame of 1, which is this one. And finally, the virtual page of 3 is mapped to the physical frame of 2. So 0, 1, 2. Now, once again, the process is not aware that paging is going on. Whenever the process wants to access an address, it'll just specify an address it wants to access. For example, process may say, I want to access address number 10 or address number 11. That address is going to be split into the page number and the offset within a page. Now, if the process says that I want to access, for example, address number 10, we can very easily, just by looking at this, conclude that address number 10 falls on virtual page 2, right, 0, 1, 2, and at the offset of 2, because 0, 1, 2, okay? So that's basically the idea. But how do we figure it out in a more robust way? Because oftentimes those numbers can be very large. Well, let's say we have this kind of thing going on. Okay, so example, and I believe there was actually a question on the review sheet that asked us that. We'll do it as part of this question. So let's say that we have the question similar to that of the slides. So suppose we have consider a system with 32-byte memory and 4-byte pages. Okay, so how big, how many virtual pages are there for each process? How many physical frames are there? And we can also do 32-byte physical memory. And let's do 16-byte virtual memory space and 32-byte physical memory with 4-byte pages. How many virtual pages are there for each process? How many physical frames are there? And let's set another question. What is the page number and offset of address? Let's pick any address. I'll just pick, okay, well, we cannot do that. No, cannot do that either. No, I'll just do 8. Okay, I'll just do 8. So now, what is the, okay. So what we're going to do is first, let's figure out how big is, how long is the address. So first, we observe that the process, since the process has virtual memory, has 16-byte virtual memory, it can access any address in the range of 0 to 15. Okay, so 16 bytes overall. Okay, so how many pages are there going to be? Well, the number of virtual pages is going to be equal to process memory size divided by page size, which will be equal process virtual memory size. So we will divide 16 bytes, which is the total memory, by 4 bytes per page, which will give us 4 pages. Okay. Now, what about number of physical frames? Well, to do that, we would basically divide the memory size by page size. Frames and pages are the same size, so the physical memory size is 32 bytes. And the page size is 4 bytes. So we have 32 bytes divided by 4 bytes per page, which will be equal to 8 frames. Okay. So now, and then the next question asks us, what is the page number and offset of address 8? Okay, so let's figure out the address length. So the virtual address length. So we need to be able to access any address between 0 and 15. Now, how many bits do we need to be able to specify any such address? Okay, so we need 4 bits, right? So we need 4 bits to specify any address between 0 and 15. Okay, so so the address length is going to be 15. Is going to be 4 bits. Now, this address is going to be split into the into the page offset and the page number. The lower bits are going to be used for the page offset, and the higher bits are going to be used for the page number. So let's take a look at that. So I'm going to convert 8 into a 4-bit number. And you can always use Python for that if you want to. I mean, though I don't really need it for 8, but just to show you how that works. So this is what 8 looks like in binary. It's 1 0 0 0. Okay. So 8 in binary is this. Okay. Now, so the lower bits are going to be used to specify the page offset. So the first question is, how many bits do we need to specify the page offset? So, well, we know that the page size is 4 bytes. Therefore, we need to be able to specify any offset between 0 and 3. Okay. So to do that, we need 2 bits. Okay, 2 bits to represent any number between 0 and 3. So we know that the last 2 bits, so therefore the last 2 bits of any address will be used to represent the page offset. The rest will be used, the rest of the higher bits will be used to represent the page number. So, as we have figured out before, 8 in binary is 1 0. So the lower 2 bits equals 0 0 equals offset 0. Okay. Now, the remaining higher bits, 1 0, is equal to 2. Okay, to page number 2. So therefore, we will be accessing virtual page 2 and offset 0. Okay, that's basically the idea. We can try, for example, another similar problem. So let's say, for example, so consider a system with with 4 gigabytes of memory, 1024 byte pages and 1024 byte pages, what will be the page number and offset of address this? Okay, I just I just literally randomly hit my keyboard to get that. So let's try to figure it out. So if you convert 4 gigabytes into bytes, and you can easily do that with Google, so 2 bytes. Okay, so it's 4 to the 9 bytes, or it's using, so basically 4 GB is equal to 1024 MB, which is equal to 1024 KBs, which is equal to 1024 bytes. Okay, so this is how many bytes this is. So 4 GB is equal to this many bytes. Okay, now the question is, how many pages will this memory space contain? So number of virtual pages is equal to virtual memory size divided by page size, which will be equal to this divided by 1024 bytes per page. Okay, so I'm going to use the Python calculator for this, divided by 1024, and this is how many pages I'm going to have. Okay, this is equal to pages. Okay, now the question asks us, what is going to be the page number and offset of this address? Well, let's figure out how many bits do we need for the offset, and how many bits are there in a 4 gigabyte address. So, well, so as we said before, 4 GB is equal to 1024 megabytes per gigabyte times 1024 kilobytes per megabyte times 1024 bytes per kilobyte. Okay, now so we have to multiply 4 gigabytes by all of this, and we can very easily rewrite this as a power of 2. So 4 is just 2 to the power of 2 times, so 1024, and you can always figure out this way if you don't remember by hand, by heart. So 1024 is 2 to the 10. Those things are always a power of 2. So times 2 to the 10. Okay. Times, and then the rest of them will be 2 to the 10. So 2 to the 10. And then again, times 2 to the 10. How many do we have? 1, 2, 3. 1, 2, 3. Okay. So, and this will be equal to basically 2 to the power of, so when we multiply, we just add the power. So this will be 12, this will be 22, and this will be 32. So it'll be 2 to the power of 32. Okay. And basically this 32 tells us how much, tells us the length of the address, because we will be able to, the length of the address is 32 bits and can be used, and we can, and process addresses can range between 0 to 2 to the 32 minus 1. Okay, 2 to the 32 minus 1. Now, how many bits to specify the page offset? And I'll put it in more detail. How many lower bits to specify the page offset? Well, the page size is, so page size is equal to 1024 bytes, and we have already figured out that 1024 can be rewritten as 2 to the 10. Okay. Therefore, so we need 10 bits to specify any page offset, and the page offsets can range between 0 and 2 to the 10 minus 1. Okay, 2 to the 10 minus 1. So this means that in our 32-bit address, so the lower 10 bits will be used to represent the page offset, and then the remaining higher bits, the remaining, I'll do 32, which is the entire address length, minus 10, which is how many lower bits we're using. It'll be equal to 22 bits will be used to specify the page number. Now, so, and the question was, let's take this address and convert it into the binary. So we do bin and 2, 3, 4, 8, 9, 7. So like that. And I'll have to add some zeros to make it a 32-bit number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So that's basically the idea. Is that 32 bits? And we can always check that in Python. But I do think I counted correctly. Yes, it is 32 bits. So now, the lower bits, so the lower 10 bits are going to be used to represent the page offset. So lower 10 bits equals page offset, which is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the lower 10 bits were used to represent the offset, and then the higher, and then the remaining higher bits, higher 32 minus 10 bits equals, are used to specify the page number. So this is the lower bits, and those are the higher bits. I'll use a different color for them. So it'll be this. And so we can either leave it like this, but I will translate that into base 10. And in Python, I can really easily do that. I can just do OB, which means I'm specifying a binary number, and boom. So we have an offset of 401, and we have a page number of 229. 229. So basically, we're going to access page number 229, and within that page, we will access an offset of 401. Okay, that's basically the idea. So do we have any questions? So so Carl is asking, how do you remember something that is that long? Oh, well, the answer is you don't. You don't try to remember it. Basically, you just understand the concept. So how to figure out the address length and how to translate the address length into the offset and page format. And then Fulia is asking, I thought lower bit size would be equal to higher bit. Can you please elaborate, Fulia? Can you please elaborate on what you mean? So the lower bits are used to represent the offset within a page, and the higher bits are used to represent the page number. Oh, I see, I see. I think you're thinking of the example on the slides. So in this case, yes, because the length of the page, the length of the address is 4 bits. And in this case, it just happens that the size of the process memory is 16 bytes, and the size of the page is 4 bits, and the length of the address is 4 bits. So it just happened to play out this way, but it doesn't have to be. Oftentimes, the page number can be much bigger than the biggest possible offset. So yeah, so it's very typical for them to be asymmetric. Make sense? But the idea is actually pretty simple. All you have to do is understand that the lower bits are always used to specify the page offset, and the remaining bits will always be used to specify the page number. And the concept is pretty simple. So first, you want to know how long is the address. Okay. So if I want to translate an address to page number and page offset, the first thing I want to know is what is the maximum length of the address in bits, and I can easily figure that out by knowing how big the memory is. So if I know the size of the virtual memory, I know the range of addresses, and if I know the range of addresses, I can easily find out how many bits I need in order to represent an address. And this gives me my address length. And then if I know the page size, I know how many bits I need to be able to represent any offset within that page. So, and basically, I reserve the lower bits of the address to specify the offsets, and then the higher bits to specify the page number. Okay, so, and Fulia is asking, so we need to get the power of 2 of the page size as the offset. There are many mathematical ways in which you can do it. I just choose to get the power of 2. One of the nice things about memory systems is that they're built around powers of 2. So things always play out quite nicely. So yeah, I like it too, because I mean, it's very simple, right? Because the power of 2 tells me how many bits I need, right? So like, for example, if I have a page, like if you tell me that the page size, like as an example, right? So if you tell me the page size, example, if the page size is, I'm just making it up, 4096 bytes, right? This implies that the addresses can range, the offsets can range between 0 to 4095, right? So, and to specify any address in this range, I will need, so 4096 is equal to, and we've already figured it out, but let's do it in Python again just to get an idea. It's 2 to the power of 12, okay? So it's 2 to the power of 12. And this power of 12, this power of 2, which is 12, tells me how many bits I need. So the power of 12, the power of 2, why am I saying 12? The power of 2 tells me how many bits, how many lower bits of the address I need in order to specify an offset. Okay, make sense? Which in this example is 12. Okay, so I need 12 bits to be able to specify any offset between 0 and 4095. Make sense? Yeah. So that's basically the idea. And if I know the address length, and then here, I'll do this. Basic examples. So this example is figuring out the number of bits, of lower address bits for the offset. Okay, so that's how you do it. And here's another example, figuring out the address length, the virtual address length. So it can go something like this. So let's say a system with, let me pick a number. Let's do maybe with 8,000 bytes of virtual memory. Well, this implies that we need sufficient bits in the address in order to specify any address between 0 and 91, right? So since 8192 is equal to 2 to the power of 13, the address length is 13 bits. Okay, make sense? So, and here's another basic example. Figuring out the number of bits to specify the page number. This could be done in many different ways. Okay, so one example is, so say many ways to do this. Okay, so let's say that system with say 64 bytes of memory and 4 byte pages. Okay, I'll keep it simple. So how many higher bits are used for page numbers. So this is approach 1. So compute the number of address bits. Well, first let's compute the address length. Compute the virtual address length, which is, so in this case, need to be able to specify any address between 0 and 63. So since 64 is equal to 2 to the power of 6, right? Sorry, wait, what? 2 to the power of 6? What the heck? That's not, oh, I'm doing multiplication. 2 to the power of 6, it'll be 64. So since 64 is equal to 2 to the power of 6, right? The address length is going to be 6 bits. The overall address length will be 6 bits, okay? Then the second thing is compute the number of lower bits for the offset. So it will be, so since the page size is 4 bytes, we need to be able to specify any offset in range of 0 and 3. And since 4 is equal to 2 to the power of 2, we need 2 bits to specify the offset. Okay? We need 2 bits to specify the offset. So, and then 3, figure out the remaining higher bits once we use the lower bits for the offset. Well, so we know the address length minus offset length, which will be equal to, so the address length is 6 bits, as we figured out in the past part, minus 2 bits for the offset, 2 lower bits for the offset, and we have 4 bits, 4 higher bits left for the page number. Okay, something like that. Okay, and there is another approach. So approach 2. So compute the number of pages of virtual pages. And we can easily do that by doing virtual memory size divided by page size. So the virtual memory size is 64 bytes. And we divide that by 4 byte pages. And if you do 64 divided by 4, you're going to get 16. So you get 16 pages, bytes per page. So this will be 16 pages. Now, figure out how many bits I need in order to specify any page number between 0 and 15, right? So since 16 is equal to 2 to the power of 6, right? 2 to the power of 6. Okay. We need, wait, no, no, it's not. It's equal to the power of 4, right? Because 2 to the power of 4 equals 16, right? What's wrong with me, folks? And that's what I warned you about. So we need 4 bits to represent the page number. And by the way, if at this point I wanted to figure out the page offset, I can easily do that, right? Because if I know how many bits how many higher bits I'll be using to represent page numbers, and I know my address length is 6 bits, I can simply do 6 minus 4, which will give me 2 bits left for the offset. Okay, does it make sense? Yeah. So it's not really that hard. It's just a concept. So which part are you confused about, Carla? Is there a more concise way to explain the whole thing? Well, it's just a concept, really. It's not a memorization thing. It's a concept. It's a concept approach, really. So you just need to understand that there is an address, and the address has a certain length, and the lower bits of the address are used to represent the page offset, and the remaining higher bits are used to represent the page number. Because remember, in paging, every single address is split into the page number and the page offset. So the lower bits are always going to be used to specify the page offset, and the higher bits are always going to be used to specify the page number. Okay, so well, it's not really an algorithm; it's like a concept. Okay, so and there are many ways to do this, and I just showed some basic examples. So for example, the algorithm version. Well, like I said, no, it's not really an algorithm. It's more of a concept. Yeah. So in math classes, you don't really necessarily work with algorithms. You would usually have to understand a concept, and this is exactly what's going on here. So, like for example, do you understand the concept of the address length? So, how long should the address be? Is that concept clear? Okay, so if we look, for example, right here, right? So if I have a system, so okay, so let's look at the very basic example again. So let's say that I have a system, right? And the system has, and each process in the system has 1,192 bytes of virtual memory, okay? So now, this means that the process should be able to access any byte in its memory, right? Starting from byte address 0, byte address 1, byte address 2, all the way to the byte address of 8191, right? Does that part make sense? Sure. So suppose you have a system that has 1,192 bytes of memory, right? Of virtual memory. So this means that the process should be able to access any address between 0 and 8191, right? Because it should be able to access byte at address 0, byte at address 1, byte at address 2, etc., all the way to the byte at address of 8190. Yeah, I mean, just like an array. Pretty much, yeah, you got it right. So and so you got that part right. Great. So now the question is, how many bits does the process need to be able to specify any address in that range, right? Because a because a binary number with a certain number of bits can be used to represent any values only up until a certain maximum value. Yeah, exactly. Bits per address. Yeah. So how many bits do you need to be able to specify any address between 0 and 8190, which is really the same thing if I ask you a question of how many bits do you need in order to be able to represent any number base 10 between 0 and 8191. Really the same question, right? Make sense? Bits per address. Yep. Does it make sense? Yeah. So, and how do we find that? Well, if we know that, so one easy way to do it in memory systems, one of the nice things about memory systems is that everything is usually power of 2. So, like we talked about just now, if the system has 8192 bytes of memory, we can rewrite that as a power of 2. And 8192 is equal 2 to the power of 13. And that power specifies how many bits we need, okay? We can also use logarithms to figure it out, but in this case, since everything is a power of 2, it's an overkill, okay? So the size of the memory is equal to 2 to the power of 13. And this power basically tells me how many bits I need to be able to specify any address between 0 and 8191. So overall, I'll be able to address 8,192 bytes whose addresses range from 0 to 8191. Okay, does that make sense? Exactly. So in this case, each address that the process will issue will be 13 bits long. Okay, make sense? Because the process will be accessing memory in the range between 0 and 91, right? Great. So you got that right. Now, so in paging, we're going to take every single address which the process issues, and we're going to split it into the page number and the page offset. Okay, so basically the page number and what offset within the page are we going to be accessing. So how do we do that split? So one example which I just talked about was right here. So the lower bits are always going to be used in order to specify the page offset. And so if my page size is 4096 bytes long, then I can specify any page offset ranging between 0 and 4095, right? Any address in that range, right? So how many bits do I need to be able to represent any address in that range? Well, the same concept applies. I can rewrite the page length in terms of the power of 2. So 4096 is equal to 2 to the power of 12. And this power tells me how many bits I need to specify the offset. Okay, is that clear? Now, let's say that you're given a, so let's say you figured out the address length and you figured out how many bits you need for the offset. Well, the lower bits are used for the offset and the remaining higher bits are used for the page number. Okay, so if you know the address length and you know how many bits you need for the offset, to figure out how many bits you need for the page number, you simply subtract the number of bits you need for the offset from the address length. And this will give you the remaining number of higher bits. And those higher bits will be used to represent the page number. What the offset means? So the offset basically means the offset within the page. So for example, so let's say that let's say that the process says I want to access some kind of an address, and so that address is going to fall on page 0, but in page 0 there are many locations. So the offset specifies basically where in page 0 does the address fall. Okay, make sense? Yeah, where it is on the page. Yeah. Make sense? Okay. Well, it's an offset. It's an offset. So basically, does it fall at 0, 1, 2, 3? Like where inside this page does the axis fall? Because pages have a size, right? So for example, if the size of my page is 4 bytes, then I may want to access either offset 0, offset 1, or offset 2. Okay, so or offset 3. Okay, so if my page is 4 bytes, I can access any offset. So either byte 0, byte 1, byte 2, or byte 3. Okay, make sense? Yeah, and there is an illustration on slide number 31. Yes. Yep, right here. Yeah. So it's a byte. Yeah. So every single address always specifies a byte. So yeah, in this case, the offset specifies the byte. So if my page is certain number of bytes long, which byte within that page do I want to access? So, and how do you find the page number? So that's what I just explained, right? So if you know the length of the address and you figured out the number of bits, the number of lower bits, you need to specify the offset. The remaining higher bits is what's used to specify the page number. So you would take the address length, and from that, you would subtract the number of lower bits, okay? And what you get is the remaining higher bits. So for example, if my address length is 32 bits, I have figured out before, and the number of lower bits reserved for the offset is 10, then the number of the remaining higher bits you use to represent the page number is going to be 32, the length of the address, minus 10, the number of lower bits used to represent the offset, and I get 22 bits. So those higher 22 bits are used to represent the page number. The page offset is specified in the lower bits. Yeah. The page offset is specified in the lower bits. The page size is always fixed. So a system is configured to use a certain page size. So the page size you will be given. So like, for example, in this example, we've been told that each page is 1024 bytes long. Okay. Which means that in this page, that within this page, the offsets will range between 0 and 1023. And to specify any offset there, you would need 10 bits. And we previously figured out that the overall virtual address is 32 bits. So to get the page number, we subtracted the number of bits we use for the offset, which is 10 lower bits, from the overall address length, which gives us the remaining 22 higher bits. So this is how many bits we have to represent the page number. I don't have to put the ones and zeros, do I? Well, so in this example, we were translating the address. We were splitting the address into page number and offset. So if you want to figure out what is the split between the page number and the page offset of an address, you basically take an address, you convert it into binary, and add some zeros if necessary in order to make the address of the proper address length. So, and then you would take the number of lower bits, which you figured out represent the offset, and that represents the offset, and then you take the remaining higher bits and you use them to represent the page number. Okay, so I have already figured out that okay, so basically, so I have figured out that it takes 10 bits, 10 lower bits to represent the page offset, right? And then I figured out that I need 22 higher bits in order to represent the page number. Are you clear on that part? So we figured out that, okay? So now, when you're given an address, you want to find out what page number and page offset does it represent. So the addresses are 32 bits. So if I convert this number, this address into a 32-bit binary number, well, I have figured out that the 10 lower bits represent the page offset. So I take the 10 lower bits, and whatever that binary number represents, that's my page offset. And then I take the remaining higher bits, and whatever that binary number represents, that represents the page number. Okay? Make sense? Yeah, it's fine if you don't convert from binary, but you could easily do that. So like in Python, for example. So if I do to convert from binary to base 10, I just type OB, and then I put the binary number, and it converts just like that. Okay. Or you can use the Windows calculator. That also works. Okay. That makes sense? Is that a bit clearer, Carla? Cool. Awesome. All right. So let's move on and let's talk about the other stuff. So the next question asked us about the TLBs. So let's talk about the TLBs. So one of the challenges with page tables is that they make everything run much slower. In fact, every single memory access actually becomes 2 memory accesses. This is because the page tables themselves are stored in memory. So as a result, whenever a process wants to access something, first we need to consult the page table in memory to figure out to what physical address the virtual address maps to, and then access the actual physical address. So each memory lookup ends up becoming 2 memory lookups, and as a result, everything runs twice as slow. So how do we get around this? This is where the TLBs come in, okay? So we're going to say that the problem that the TLBs are trying to solve is the fact that page table is the following, okay? And I will copy it and paste it from the slides. Okay. So is that which is slow, okay? So solution is use a TLB in order to cache a subset of page table entries, okay? So the TLB consists of two, I'll say TLB is an associative memory that caches the page number and the associated physical frame number. Okay, whenever the process requests a page number, first the fast, the TLB is probed, and if the page number, if the page to frame mapping is present in the TLB, we get the physical frame number from the TLB. This is known as the TLB hit. TLB hit, okay? Otherwise, if the mapping is not present in the TLB, then the page table is probed, okay? That's basically the idea. So TLB caches a subset of entries from the page table in order to speed up the virtual to physical resolution, okay? That's basically the idea, all right? So now, the second, so let's take a look at the picture of the TLB just to remind ourselves what it looks like. So TLB is basically an associative memory which has the page number and the associated frame number. So whenever a process wants to, whenever a process issues the virtual address, it'll be split into the page number and page offset. And first, we're going to probe the TLB to see if the associated, if the page and its associated physical frame are cached in the TLB. And TLB is a piece of hardware which allows me to compare all of the page numbers in parallel. And if one of the page numbers matches, then we have a TLB hit and the physical frame number is gotten quickly from the TLB. Otherwise, we have to, on a TLB miss, we have to probe the page table, okay? That's basically the idea. Now, the next part of the question asks, why must a TLB be flushed on each context switch? So let's talk about that. So the TLB must be flushed on every context switch because each process has its own page tables, okay? Because each process has its own virtual memory. Context switch, so that was a part of the midterm. So context switch is when we switch the CPU between processes, okay? Sure. So, okay. The context switch is when we switch the CPU between processes. Oh, yes, definitely. I mean, context switch is very fundamental. So, and it was covered by the first exam. So, yeah, I mean, it's really important to know that. So, yeah, so TLB must be flushed because each process has its own page tables, its own page table, and the TLB caches entries from the page table, okay? The context switch is when we switch the CPU between processes. Since the new process has a completely different page table with pages mapped to different frames, TLB must be flushed from the page mappings of the previous process and populated with mappings from the new process, okay? That's basically the idea. To avoid having to flush the TLB on every context switch, we need to extend the TLB with address space identifiers, or ACIDs. ACIDs. Okay, like that. So each process has an associated ACID, unique ACID. So whenever the process, whenever the process issues a page request, the TLB is going to be probed, and the process ACID, as well as the page number, will have to match in order to have a TLB hit. Okay, so in other words, ACIDs allow the TLB to differentiate between the entries of, or I'll say mappings, between the mappings belonging to the different processes. Okay, and this is the picture of the TLB extended with ACIDs. So whenever a process wants to access a page, the process ACID will be matched as well as the page number. And if both match, then we grab the associated physical frame. Okay. And this way we can avoid having to flush the TLB, because now TLB has a way of telling the difference between the page to frame mappings belonging to the different processes. Okay. That's basically the idea. Okay, so those are the TLBs. Any questions? Okay, so let's talk about protection. So how do we implement protection in page tables? So let's take a look at that. So we can basically implement protection as follows. So with each page, we can associate a read and write bits, which specifies whether the page is readable and or writable. So for each page, with each page in the page table, we can associate read and write bits. If the read bit is set, then the page is readable. If the write bit is set, then the page is writable. Okay. In addition, we can associate each page with each page the V bit, the valid invalid bit, okay, which specifies whether the page is part of the process memory. That is, does it have an associated valid physical frame? Okay, that's basically the idea. All right, makes sense. And then the next question asks, what is a page table pointer and what is it used for? So let's talk about that. Okay, so the page table pointer is a pointer that points to the process page table. PT page table pointer. Okay. So as we said before, each process has its own page table, and that page table is stored in memory. So whenever we switch processes, whenever we do a context switch, we want to tell the CPU which page table to use. So PTBR is the page table pointer, which stores the pointer to the process page table. So during the context switch, the PTBR pointer is switched to point to the page table of the currently running process. Okay. Next, let's talk about the page table types. For example, what is a hash table? How does it work? What are the advantages? What are the disadvantages? So before we talk about the different types of page tables, let's learn why we need different kinds of page tables. So in class, we have primarily focused on the traditional page table. So in other words, a page table has an entry for every virtual page, and it is indexed by the virtual page number. And the index location contains the corresponding physical page. Now, although this kind of page table is very easy to implement and is very easy to understand, it does have some downsides. And the downside of it is that it requires a significant amount of contiguous physical memory. This is because the page table itself is stored in memory, and a page table like this that can be indexed, it has to be stored in contiguous memory. In other words, each entry has to be stored contiguously one after the other so we could index. So just how much contiguous memory would we need in some cases? Well, imagine a system where you have a process where each process has 4 gigabytes of virtual memory. This is how many bytes that is. And let's say that the size of each page is 4096 bytes. How many entries will this page table have? Well, the page table will have as many entries as there are virtual pages. So how many virtual pages will there be? Well, we simply take the overall system memory, how much virtual memory there is, and we divide that by the size of a single page. So how many pages do we get? We get this many pages. So this is how many entries there are going to be in my page table. That's a lot of entries, okay? So this page table will require a significant amount of contiguous memory. Now, just how much contiguous memory will it require? Well, let's say that each entry is 4 bytes in size. So if this is how many entries we have and each entry is 4 bytes in size, then the total memory used by the page table, and I should point out total contiguous memory used by the page table, is going to be number of entries times size of each entry, which will be equal to this times 4. Bytes per entry. All right. So what will this come out to? So this is what it will come out to. So this is how many bytes per page table we'll have. This is how big our page table will be. This is how much contiguous memory it will require. Now, this isn't bytes. To get a better idea, we can always convert it into megabytes. So, for example, bytes to megabytes. So it'll require 4 megabytes of contiguous physical memory. That is a lot, okay? Which is same thing as roughly 4 megabytes of physical memory, which is a lot of contiguous physical memory. So the point of this whole calculation is just to show you that the traditional page tables, they require a significant amount of contiguous memory. And once again, it is so we can index into them, okay? So to enable indexing, each entry has to be stored one after the other. So how can we reduce the amount of contiguous memory that we need in order to store a page table? Well, that's where different types of page tables come in. There are alternatives to the traditional linear page table like the one we have right here. So let's take a look at them. So there are 3 different kinds of page tables besides the traditional linear page table, which is the hierarchical page tables, hashed page tables, and inverted page tables. Let's take a look at the hierarchical page table. So the basic idea behind the hierarchical page table is that in order to reduce the amount of contiguous memory that we need to store a page table, we're going to split one big flat page table into a page table that has multiple levels. That is, there is a outer page table, and each entry in the outer page table points to another page table. And then each entry in that page table actually contains the resolution of the virtual address to the physical address. Now, this is a 2-level page table. So there is an outer page table which contains pointers to a bunch of second-level page tables. And finally, the page table at the second level actually stores the physical frame that is associated with the virtual page. This can go on for multiple levels. It doesn't have to be 2 levels. We could have a page table, for example, that is 3 level or even 7 levels. All right. So the problem with the hierarchical page tables is that although they indeed can help to reduce the amount of contiguous memory that we need to store a page table, and once again, that is because we're splitting one big page table into a bunch of page tables. Okay, so there is an outer level page table. Each entry contains a pointer to another page table, and then that page table actually stores a resolution of the virtual to physical page. Now, another remark about hierarchical page tables is that in hierarchical page tables, the virtual address is going to be split into 2 page numbers and a offset. And this is specifically for a 2-level page table. So the first page represents an index into the outer page table. The second page represents an index into the second-level page table. And finally, the lower bits represent the offset inside the physical frame. Now, the problem is if this goes on for many levels, this can result in hierarchical page tables being really slow. Remember how we said that even with traditional page tables, each memory access becomes 2 memory accesses. This is because whenever a process issues a virtual page request, we have to first translate it using the page table, and then based on the physical address that we get, then we access the physical memory. Well, the issue is that page tables themselves are stored in memory. So every memory access becomes two memory accesses, because first we have to, whenever a process issues an address, we first must look it up in the page table and then take the physical address from the page table and use it to access the actual physical memory. So that's just for the traditional page table. Now here, each memory access actually becomes three memory accesses, because first I have to consult the outer page table, then the inner page table, and then I have the actual memory access. So everything, all memory accesses, run 3 times slower. If I have more levels, they'll run even slower. For example, a 7-level page table where everything is going to run, well, 8 times slower, because I would have to first look up my address in 7 page tables and then finally use the physical address in order to access the actual physical memory that I want to access. So that is basically the idea. So now let's take a look at the hashed page table, which tries to address some of the problems associated with the traditional flat page table. Another way to try to reduce the amount of contiguous memory required to implement a page table is to use a hashed page table. So a hash page table is basically an attempt to implement a page table as a hash table data structure. A hash table data structure is basically an array of linked lists where each element of the array is a linked list that represents all of the items that are mapped to that location. So typically in a hash table, whenever we are given a value to insert into a hash table, we're going to compute a hash function of that value. So basically the hash function will take the value and it is going to convert it into a value that represents some index in the array. It is possible for multiple values that are different to be mapped to the same slot in the array, because the hash function will convert them into the same value. So all of the values that hash to the same place will be entered into a linked list in that location. So in a hashed page table, our page table will go from 0 to some maximum length n, and then whenever a process wants to access a virtual page, we're going to run the page number through a hash function, which will map it into an index in this hash table, and then we're going to search the linked list located in that index to find an entry where the virtual page number matches the page number requested by the process. And once again, it is possible for multiple pages to have entries in the same index, because different page numbers may hash to the same location. So this location contains all of the virtual page numbers that are hashed to the same location. Each node in the linked list has a virtual page number that hashes to this location along with the associated physical frame. And there's a pointer to the next element in the linked list. So when a process issues a virtual page request, we hash the page number. We use the output of the hash function in order to index into the array. And then we're going to search that slot until we find a virtual page number that matches the page number requested by the process. And when we find a match, we'll take the associated physical frame number stored in the same node, and that becomes our physical frame number. So by constraining the size of our hash table, we can limit how much contiguous memory we need in order to store the page table. Okay, so that is basically the idea. Another approach to implementing a page table is called the inverted page table. So the inverted page table is just the opposite of the traditional page table. In a traditional page table, there is an entry for each virtual page of the process. In the inverted page table, there is a single entry for each physical frame. So you can think of the inverted page table as an array where each index location represents a physical frame number. And inside each element of the array, there is the process ID and a virtual page that is mapped to the physical frame represented by that location. Let's take a look at how this actually works to get a clear idea. So once again, a inverted page table is basically a page table where there are as many entries as there are physical frames in the system. Okay, so and each element of the inverted page table contains the process ID and a virtual page that is mapped to the physical frame represented by the location I. So in other words, if this entry is found at the index location I, it means that process with PID, process with this PID has its virtual page P mapped to the physical frame I. So once again, the index location itself, the index of this entry represents the physical frame, and the contents of the entry represent the process for which this mapping applies, and the virtual page number to which the physical frame I is mapped to. So that's basically the idea. So how do we do lookups in the inverted page tables? Well, we have to search the entire page table until we find the entry which matches the process ID of the process that has requested a virtual page and the requested virtual page. So we're going to linearly search this array until we find an entry where the PID matches the PID of the requesting process and matches the virtual page number of the requested page. If we find this match at index location I, then I represents my physical frame number to which page P of process with process ID PID is mapped to. So once again, P is mapped, virtual page P is mapped to physical frame I. And we're talking about the virtual page of process with ID of PID. So unlike with traditional page tables where there is a separate page table for every process, in case of the inverted page table, there is a single page table for the entire system. It stores the mappings for all of the processes on the system. The downside of the inverted page table is that shared memory is kind of difficult to implement, and this is because in the traditional page table, we can two processes, they can share memory by mapping their virtual pages to the same physical frames, and virtual memory and shared memory is implemented. This is difficult to do with the inverted page table because there is only one page table and it maps frames to pages, not pages to frames. All right. Also, searching the page table thus can prove to be kind of slow. Okay, definitely much slower than doing a simple index operation in the traditional flat page table. So that's basically the idea. Now, the next question asks us, page sharing, how does it work? What are the advantages? And give an example. So let's talk about that. So page sharing is a way to optimize memory usage. For example, consider a case where I start multiple instances of the text editor. Now, each text editor is going to be editing a different document, so the memory pages containing the data of those documents is of course going to be different, and each one will require different physical frames to store that information. However, the codes of both processes, the codes of all the instances are going to be the same, because the executable code of programs generally doesn't change. It is read-only. So this means that the physical frames that store the code of the editors don't have to be duplicated. We can simply allocate one set of physical frames which will store the code of the editor, and then all of the processes, all of the editor processes are going to map those physical frames into their memory using their page table. So this way, we won't have to duplicate the identical pages many times. Let's take a look at how this will work in practice. So we have started 3 instances of the editor process, and it looks like each editor has 4 pages. Those are the page tables of each editor, and this is the physical memory. So the first 3 pages, they contain the editor code. Okay, they contain the code of the editor, and then the last page contains the data that is being edited. So what we can do is, into the physical memory, we can load the code of the editor only once. So we're going to, for example, allocate physical frame 3 to store the first page of code. We allocate physical frame 4 to store the second page of the editor code, and we allocate physical frame 6 to store the third page of the editor code. So, and all of the instances of the editor process can now share this code by mapping it to their memory using the page tables. So how do they do that? Well, in editor 1, in its page table, for page 0, it maps it to physical frame of 3. So this is page 0, and when we index to the location 0 in the page table, we see that it's mapped to the physical frame of 3. Page number 1 of the editor process is mapped to the physical frame of 4. Page 2 of the editor is mapped to the physical frame of 6. And you can see the other 2 editors doing the same thing. So for the second editor, it also mapped its page 0, which contains the first page of the code, into physical frame 3, which is the same as what this process did, which is the same as what this process did. Similarly, all 3 processes have mapped their second page, which is page 1, onto physical frame 4. Okay? Similarly, the third page of each process was mapped to the physical frame of 6. Okay? Now, finally, the fourth page of each editor is actually mapped to a different physical frame. So page number 3 is mapped to the physical frame 1. For this process, it is mapped to the physical frame of 7. For this process, it is mapped to the physical frame of 2. And this is because all of the processes are editing different documents. So those different documents require different physical memory locations to store them. They cannot share the data. However, since all of the processes have the same code, we can allocate a set of physical frames that will store the code for the editor, and then that code is going to be shared by all 3 instances of the editor process. And once again, this sharing is achieved by each process mapping the same set of physical frame into their memory via their page tables. So that's basically the idea. Another technique which can be used in order to save some memory resources when you create a new process is the idea of copy and write, also known as COW. So imagine that you have a parent process, and the parent process has just created a child process. We have previously talked about the fact that the child memory is basically a copy of the parent's memory. Now, if you think about this intuitively, you may imagine that when you call fork, basically every single physical frame of the parent gets cloned. In other words, we create copies of all the physical frames of the parent, and we give those copies to the child. This would work, but this could prove to be somewhat wasteful sometimes, because it is true that eventually the parent and child will start modifying their memories, and their memories will look different. However, a lot of the memory pages of the parent and child will likely remain the same. So what we're going to do is we're going to, when the parent forks a child, initially the parent and the child, they will share the same physical memory frames. So in other words, the child's page table will basically map the same physical frames as the parent's table. We're not going to create copies of any physical frames and assigning them to one process or the other until that respective process modifies it. Let's take a look at an example to get a clearer idea. So let's say this is the parent process and this is the child process, and this is the physical memory. So initially the parent process has mapped physical frames A, B, and C. Now the parent has forked a child, and this is what the initial page table of the child will look like. So basically parent and child, they share the same physical memory pages. We're not going to make copies of any of those pages until one of the processes actually modifies one of those pages. This is why it's called copy and write. We create copies of frames only after they're modified. So now let's say that the parent now modifies frame C. What is going to happen? Well, when the parent modifies the frame C, what's going to happen is a copy of frame of this physical frame is going to be made. This is where we allocate a new physical frame, and into that frame we copy the original contents of this frame, and then we allow the parent process to modify it. So now, after the parent has tried to modify page C, the parent and the child, they now share frames A and B, but they no longer share the page C. And the reason for this is because A and B are the same for both processes, but C is no longer the same for those processes. So that's why the parent gets its own copy. So once again, the basic idea behind copy and write is that we're not going to make any copies of the memory. We won't be making any copies of physical memory until the memory is modified. Okay? That's basically the idea. We only create copies of physical frames when they're modified. Okay? So once again, you have a parent process, you have a child process. This is what their page tables look like right after the fork. So when the parent forks the child, both of their memories are the same. So instead of making a copy of each physical frame of the parent and mapping it to the child, we will delay doing so until one of the processes modifies one of the frames. So the parent forks the child, and initially, until their memories start to diverge, the parent and the child, they will share the same set of physical frames. Only when one of the processes modifies its a physical frame, only then will a new physical frame be allocated, the contents of the original frame will be copied into it, and the process will be allowed to make changes to it. So now the parent and child, they still share physical frames A and B because they're the same for the parent and the child. However, they no longer share the frame C because the corresponding pages are now different for the parent and the child. So this helps to save some memory. The next question asks about segmentation. What is segmentation and how is it different from paging? What hardware support is required? So let's talk about that. So in class, we talked about segmentation. It's an alternative approach to memory management and is different from paging. So basically, what segmentation does is that it divides the virtual memory into a bunch of variable size segments, and each segment represents a particular part of the process memory. So for example, we can have one segment that represents a certain subroutine of the program, another one to store the stack, another one to store the main program, another one to store some kind of a square root function, and another one to store what's called a symbol table. Now, each of those virtual segments is going to be mapped to an actual segment in the physical memory, and each segment is assigned a segment number. So, in order to implement segmentation, we need special hardware. So first of all, each address in segmentation will be represented by a segment number, which represents the segment which we would like to access, and the offset within the segment that we would like to access. So once again, when a process wants to access a certain memory address, it'll specify the segment where that address is located and the offset within the segment where that item is to be found. Now, in order to be able to translate from virtual addresses, which look like this, into the physical addresses, we need something called a segment table. A segment table is a data structure that is indexable by the segment number, and each location in the segment table contains two things. First is the segment base, which contains the physical address of where the segment starts in physical memory, and the segment limit, which is how big that segment is. To convert this virtual address into the physical address, we look up the segment base in the segment table by indexing using the segment number, and then to the segment base we add the offset, and that becomes the physical address. And it is very important, by the way, that offset is not greater than the segment limit. Otherwise, you go out of the limits of the segment and you get what's called a, well, segmentation fault. So let's take a look at a picture of how this looks like in practice. So a process is executing on the CPU and it issues a virtual address. So once again, the virtual address consists of the segment number and the offset within the segment. So we're going to use the segment number in order to index into the segment table, and we're going to look up the base, which is the physical address in memory where the segment begins, and we're also going to look up the limit, which is how big the segment is. Before we try to translate the virtual address to physical, we're going to check to make sure that the offset, which we like to access within the segment, is less than the limit, which is the size of the segment. And if it is not less, then you have basically a segmentation fault. Otherwise, if the offset is less than the limit, we're going to convert the virtual address into physical by taking the base, which once again is the physical address where the segment begins in physical memory, and to it we add the offset. And that gives us the physical memory address that we're going to be accessing. Let's take a look at an example to get a better idea. So here is a program which has 5 segments. Each segment has a number from 0 to 4. And this is our segment table, which maps the virtual segments to the physical memory. And here is our physical memory and where each respective segment is stored. So for example, segment number 2 starts at the physical memory location of 4300 and its size is 400. Okay, we simply index into the segment table using the segment number to find out its base and limit. Now let's take a look at some examples of how this virtual to physical translation actually works. So let's say that a process wants to access offset number 53 within segment number 2. Well, we take the segment number, we index into the segment table, and we see that the limit of the segment is 400. First, we want to check to make sure that the offset which the process wants to access is less than the limit. And 53 is indeed less than 400, so this is a valid offset. In that case, we can convert this virtual address into the physical address by taking the base, which is the starting physical address of segment number 2 in memory, and to it we add 53. And 4300 base plus 53 offset is equal to the physical address of 4353. So we will end up probably accessing something right here. Let's take a look at another example. Suppose the process wants to access offset 852 in segment 3. Well, we index into segment number 3 in the segment table using the segment number. We see the limit is 1100, which is less than 852. And to convert it to the physical address, we add the offset, which is 852, to the base, which is 3200. So we get a physical address of 4052. Let's take a look at the last example. So here we have a process that wants to access offset 1222 in segment 0. Well, we begin by indexing into the segment table using the segment number of 0, and we check if the limit, which is 1000, is less than 1222, and it's not. So therefore, we have a segmentation fault. So that's basically the idea. And then the next one asks us, and what is the difference between segmentation and paging? So segmentation divides the memory into a bunch of contiguous segments, and it resolves virtual to physical using the segment offset format rather than page offset. And segmentation divides memory into a bunch of variable sized segments. Okay, so the segmentation is an alternative to paging. And unlike paging, it divides the virtual and physical memories into segments of variable sizes. Paging divides memory into equal sized pages. The virtual addresses are then represented using the segment offset format. Okay, that's basically the idea. Okay, and what hardware? A segment table hardware is needed in order to support this scheme. Okay, so each entry in the segment table consists of the segment. So the segment table is indexed by the segment ID, and each location contains the base physical address of the segment and the limit, which is the size of the how big the segment is. Okay, so that's basically the idea. Okay, and then the next question asks, what is a page fault? Okay. So basically, the page fault happens in demand paging. So demand paging basically means that that in order to save memory and to allow processes to have a more virtual memory than there is available physical memory, we can temporarily keep some process pages on the disk without actually allocating physical frames in RAM until that page is needed. So to implement that, we can use a page table, and we're going to be using valid and invalid bit. So valid bit means that the page has an associated physical frame. So for example, here, page index 0 has an associated physical frame of 4. And it's valid because the valid bit is set. Same thing with page 2 that has an associated physical frame of 6, and page 5, which has a associated physical frame of 9. So if the process tries to access page 0, we see that it's set to valid, so we just grab the corresponding physical frame. Otherwise, if let's say the process decides to access page 1 and the bit is set to invalid, then it means that if the access is valid, the associated page is not stored in the physical memory, but rather is on the disk. In this case, we need to load the associated page from the disk into a newly allocated physical frame. So here is how that is going to work. How do you actually service a page fault? So page fault means we're going to be bringing a page from the disk into the physical memory because it is needed. So whenever a process tries to access a page whose valid invalid bit in the page table was set to I, a page fault is going to be generated, and the associated page is going to be brought in from the disk. So what is going to happen is that the operating system will validate the page access to make sure it's valid. And if this is invalid access, then abort. If the access is valid, but the page is not in memory, we will continue on to step 2. So we will allocate a physical frame in the RAM. We will load the contents of the page from the disk into the newly allocated physical frame. We're going to update the page table in order to map the frame, to map the virtual page that generated the page fault to the new physical frame. We're going to update the valid invalid bit of the page table to V. And finally, we're going to restart the instruction that has caused the page fault. A pictorial representation of this looks like this. So a process executes an instruction that wants to access a particular page. A page table is consulted, and we find out that this virtual page in the page table has an I bit set. So what's going to happen is the operating system is going to be summoned, and a new physical frame will be allocated. That physical frame is going to be filled with the page contents loaded from the disk. The page table is going to be updated to map the page to the newly allocated physical frame. And finally, the instruction is restarted to try the access again. Okay, that's basically the idea. Okay, so and this is basically, this is basically right from the slide. So I will basically say, so like, so instead of doing copy and paste, I'll say C, oops, C slides. What is it? 65 to 68. Okay, 65 through 68, because this is essentially copy and paste. So I'll just put that down there instead of copying and pasting all of the slides. And thrashing, which is the next question, is a related concept. Okay. So what exactly is thrashing? So thrashing happens when the process is constantly paging in and paging out. Imagine that the process doesn't have enough physical frames. In fact, most of the physical memory is full. So as a result, in order to be able to accommodate all of the processes, so let's say that processes want more memory than we have physical frames available. Okay, so in that case, some of the frames will have to be stored on the disk, and some will have to be stored in the physical memory. Now, let's say this happens. So let's say that part of the process memory is on the disk and part is in the physical memory. Let's say the process wants to access a page that is on the disk. Well, in that case, we will have to take one of the physical frames that is already mapped to the page of a process, possibly another process, save its contents onto the disk so we can free the physical frame to store the page, to store the incoming page of the process. So one physical frame will be freed by saving it to the disk, and then into the physical frame, we're going to save the contents of the page from the disk that was requested by the process. And then let's say that the process now requests another page that also happens to be on the disk. And maybe it is the same page as before. Okay, so process wanted to access page A. Page A was on the disk. So we had to free the frame associated with page B by storing page B onto the disk. So we can bring in page A. And then shortly, right after, the process now wants to access page B. Well, now to free physical memory, we have to take page A and we have to save it back to the disk and then bring back in page B. So in other words, thrashing is when the process is spending most of its time paging in and paging out. So in other words, it's saving pages onto the disk just to shortly have to bring them back into the physical memory. And it happens when the process doesn't have enough available physical memory, so it constantly has to save part of its memory onto the disk just to bring those pages back very soon. So as a result, the process spends most of its time paging. And because paging requires disk I/O, the process gets very useful work done. Yep. And the reason why it's called thrashing is because the way in which it manifests is when you look at your disk, you'll see the disk is constantly grinding, but the process seems to be stuck, okay? Because it's constantly paging in and paging out. So basically, page fault after page fault after page fault, because the process keeps saving part of its memory onto the disk, and then in a short while it needs that memory again, so that creates page faults, and we have to now take another part of the process memory, save that to the disk, so we can free up some memory, so we can bring in the pages which are required right now. So that's called thrashing, okay? And thrashing results in a low CPU utilization because the process spends most of its time paging, and paging is I/O. The CPU is not really being used much, and sometimes this can trick the scheduler into making things worse, because the scheduler can say, oh, the CPU utilization is low. Well, how do we deal with that? Well, we can bring in more processes to better utilize the CPU. But the problem on why the CPU utilization is low is because a process is thrashing. And it is thrashing because processes are thrashing, and the reason why they're thrashing is because there is not enough physical memory available. And the way to increase the amount of available physical memory is not to add more processes. That'll do just the opposite. Okay, so that's basically the idea. Okay, so thrashing is basically this. Okay, so a process is okay. So that's basically the idea. All right, folks. Good luck on the exam, and you can do this. And if you have any questions, feel free to let me know. And as I always say, peace.